Hello. And welcome to a recorded demo, made by IZT and IMPO RF. The demo includes short presentation of IZT capabilities, recording, monitoring, receivers and direction finding, including a short demo of a direction finding software. For any inquiries, feel free to contact us.
Okay, so we have antennas. We build our own. We design, simulate, and build our own antennas. At this point, we have a 9-element stationary VHF/UHF antenna, and we have a mobile antenna, also 9 elements from 20 megahertz to 6 gigahertz, intended for applications on vehicles. We have a fairly broad range of DF receivers. We have a 9-channel DF receiver VHF/UHF with 40 megahertz instantaneous bandwidth. That's very high performance equipment with direct sampling and digital signal processing in the receivers, and it's intended for our VHF/UHF DF system. We have a 5+1 channel system up to 6 gigahertz with 60 megahertz instantaneous bandwidth. We have under development a 9-channel VHF/UHF system with 400 megahertz instantaneous bandwidth. It is maybe to explain the nomenclature here. So light green is under development. Dark green is on the roadmap, but it hasn't been started yet. We are also developing a ELINT DF system with 240 megahertz instantaneous bandwidth up to 18 gigahertz and with 18 synchronous channels. We also have on our roadmap to integrate a receiver right into this mobile antenna so that it can be connected to the DF processor just via a hybrid cable. We already have this realized for our 60 megahertz version, so this can go right into an antenna and is then connected via a hybrid cable to the DF processor. We have profound experience on signal distribution networks for whatever purposes, also for airborne applications with the DO 160 certification. Then we have our monitoring receivers. Stefan already elaborated on those. 24 megahertz instantaneous bandwidth, 60 megahertz or 120. We have I'm just seeing this slide is wrong. We also have a very high performance HF receiver in our portfolio. We have additional equipment like frequency, references, distributions, etc., to build larger systems. Once we complete this development, this will also lead to a single channel 240 megahertz wide receiver at some point.
Do you have receivers both for monitoring and DF?
Doesn't matter. The DF is basically always a conglomerate of monitoring receivers which are synchronized.
So if I wanted both monitoring and DF, I would need 2 receivers, one for monitoring and one for DF.
Not necessarily. It would also be possible, or it is possible, to take the DF receiver, which is sampling all 5 or 9 channels, and also to digitally calculate narrowband channels from this broadband signal. So that is possible. Sometimes customers want independent tunable monitoring and DF. For example, they use the DF part to scan the band, and then they want to monitor constantly frequencies of interest. Then they need separate hardware or separate local oscillators, which is the case in such a receiver, which is 5+1 channels. So this has, in this example, a 5-channel DF receiver, fully synchronized, same LO, and an independently tunable fixed channel for monitoring. So it depends on the architecture. For us, these are just building blocks. They are, it's all the same hardware modules, basically. In terms of DF software, we have a software which is rather lean for ATC, air traffic control purposes, and vessel traffic, naval vessel traffic coordination. Rather lean software. And we have a more powerful comment DF software, which we will give you a short demo afterwards. And we have a development ongoing for a ELINT DF software for short pulsed signals, together with the antenna. We do have monitoring software. One element which we are selling quite successfully is satellite network monitoring, for basically assessing capacity and interference situations on a satellite network. We can do broadband IQ recorders and post-processing, AI-based segmentation algorithm for basically identifying or separating the broadband spectrum into individual narrowband transmissions for further processing.
Does that require any prior data? Is it supervised?
The segmentation has been trained by us. Yeah, because I've made the experience that doing an agnostic segmentation is not a proper solution. We have an anti-surveillance system for 2 of our government customers, basically to identify, let's say, unusual signals in a building complex. We have an add-on to our monitoring software for time difference of arrival location finding.
How do you synchronize the receivers?
GPS.
What happens in a non-GPS environment?
We have a receiver version which has a rubidium standard, and for this customer we specifically implemented this rubidium standard because when they are in a building, they do not necessarily have GPS coverage. So what they do, they basically gather the receivers at a common location, hook them up. Then it will take hours for the receivers to synchronize the rubidiums. They have batteries built in, and then they disconnect the receivers and carry them to the locations where they want to use them, and they will stay within adequate synchronization as long as the rubidium.
Can you advise more on TDOA?
Yeah, you need a network. Time difference of arrival has, as you certainly know, certain limitations. First of all, you need bandwidth in the signal, otherwise you cannot measure, and you need some backhaul. Our software does local caching in the receivers, so it is not necessarily required to have a backhaul with a lot of throughput, but you need some backhaul. Well, it works with, let's say, commercially available LTE or mobile connections. If you have more bandwidth, you get a better accuracy. But I would say that the amount of data you have to transfer is proportional to the accuracy you want to achieve and you can achieve. There is a practical limit based on the SNR and signal bandwidth, of course. But the backhaul speed mainly determines the software, and it can be a server at the site will cache the whole bandwidth, and the command station will have to define what signals are to be located. And then it basically, the command station issues a remote control to the slave stations. They will extract the signal from the recording and let's say send its fingerprint back to the central station, and then this will calculate the location estimate. Yeah, it's a manual operation. TDOA can never get near AOA just for the sheer amount of data. So I say TDOA is a nice add-on to a monitoring network, but it cannot replace AOA DF, and the hybrid DF, let's say several DF AOA stations can be complemented with TDOA, but it's only a poor man's DF. Okay, so we can do TDOA. We also have the provisions for FDOA if there are enough nodes available. We have a development for separating carrier and carrier signals. That is, let's say, the preliminary stage that's intended for separating satellite signals which share the same channel or two directions. We are also developing ELINT monitoring software, but only down to the pulse descriptor words. The rest is done by our customer. In terms of control software, we have result viewer, missions and tasks. At some point, and we have, let's say, a limited geolocation network capability. Basically, if you're combining the DF results from multiple stations. I mean, that is actually a screenshot from our TDOA system where you can see the hyperbolas, and we also have this for AOA, but it's not yet a full geolocation network. Well, the DF will process the full spectrum. In order to get a location fix, the operator has to pick a frequency. It would not be magic to, let's say, do this automatically. It's some complexity, but I mean, we can segment the spectrum, we can DF a spectrum, so it could also be overlaid to location information for every signal segment that has been found. Absolutely. If you want location fix for frequency hoppers, Yeah, they need to be synchronized, but they are synchronized anyway. So all our receivers work off fixed time basis. So as long as we have a common timing reference, like for example GNSS or a good holdover, there's always timestamp in every data. So that comes with it. Okay, in terms of systems, what have we implemented? We have built a network of ATC direction finders. We are now about to build a network of vessel traffic system direction finders. We have built stationary common systems with DF. We are building a mobile RDF for government customer. We have built several shortwave HF DF systems, fairly large arrays, and we are working on an ELINT system, which will go on top of our container, on top of a vehicle. So it goes on the radome. Like it's basically this thing without the radome, and this is designed to go on top of a vehicle. Or also we made sure to limit the weight, so it could also go on a telescopic mast. Okay, so this is basically our anything which has to do with intercepting signals. We have signal generators for like broadcast standards for comment testing, comment stimulation, also for GNSS satellite emulation. Neil is very knowledgeable about these things now. And we have a range of equipment for link testing. It's mainly for satellite links. Sometimes people also use it for aircraft to ground links or interstellar vehicles, basically to test the telemetry or the communication links. Then some other small stuff like link 11, link 22, test devices where we have a contract with NATO. As we call search receiver, it's being tasked by the operator once, then it will automatically capture, do continuous broadband buffering of the whole bandwidth that has been specified, will automatically do the segmentation. We have a video afterwards, and then produce the results, and then they can be accessed.
Yeah, and we have a short video here which shows both the AI segmentation and also how this is then analyzed and decoded. So basically what we see here is now that that's the signal suite. You see the spectrum below. I would stop the video for a moment. You have an NRT noise writing threshold, lightly blue, which is behind. You can change the order, which one you want to see first. So behind the spectrum, the blue line here is the noise writing threshold, and then the AI segmentation detects signals. So this one is a 20 meg, so that's an R3000 receiver. But here in the receiver corner, you see that this one is limited to 5 megahertz. Yeah. So out of the 20 megahertz, we are now, if I scroll forwards, we are now analyzing 5 megahertz. We're doing the segmentation, the automatic segmentation of 5 megahertz signal here. The upper screen is a time, power and color frequency view, and below you see the frequency and power level view. So the upper part is basically the time. And now if I stop again, you can see here that now the AI segmentation has marked certain signals which were identified as being signals. So I will leave it running because the colleague now zooms into the area, and now you can see the white dots are basically where our system has identified signals, and these will be soon. If we wait another, it's working in certain blocks. So soon they will add, because the AI has detected the signal is still present. So we get refreshed every, let's say, 18 seconds here. And now, as a next step, an automatic classification and demodulation of these signals will take place, which will follow shortly. So here you see how the AI identifies these signals. And now here we see classify results. So PSK modulation, center bandwidth, duration, and we get information, static was detected. And then out of these production results were generated. So here you see, seems to be a French person here, Voulez-vous le brick? So you also get decoding as long as we have a decoder available to this. And this is basically prosaic result viewer, where you can, all the results which were identified, they are still present, where you can look them up and find more information on them. So this is basically the search receiver, including the AI segmentation.
Instead of just the, do you see now?
Yes, now it's there.
Yeah. So this is a little toy recording with 40 megahertz bandwidth here that's analyzed, and so we have our own DF processor that is able to calculate the directions, and I can show them here. Now here, right now, we don't have a signal, so we have a very scattered angle field. And when we hit play, like here, we started an actual signal. You can see now here we have a proper angle, about 33 degrees. So we can zoom in a bit on this signal, and we can also show the angle in a polar display. This is now with a rather large standard deviation, because you have some outliers here. So also for this, we have a clustering algorithm. If we put this mode here to smart, it will throw out these single outliers, and we will have a rather sharp bandwidth, and we will also be able to use the whole bandwidth here. So I can set the bandwidth here a lot higher now, and just use the whole angle field here. That's sort of reliable. And here we have this direction more or less. For this clustering algorithm, we can also mark ATF emission and show the results. So this is now averaging over all the angle values out of this marked rectangle. Before it pretty much looked at the current time step, and it can also show on a map here where the direction is coming from. And then the next one will be from a different location. So this down here is from a different direction. It's from down here. And you can see the angle here. For this, we also have an automatic detection. For this, I will reset to the start and add the DF segmentation. And if I play now, then once we arrive at defined angles, now we have the defined angles, it will automatically search for matching DF emissions and will mark these. Right now it's now it found and matched the angles. So it says like in this emission we have more or less an angle of arrival that matches, and here again we have an angle of arrival that matches, and this one here, if I pause quickly.
Okay, now the DF can of course monitor moving targets. So in order to give you an idea, we had our small 5-channel DF on our roof, which is a 3-story industrial building here in the southern part of Erlangen. Then we did a drive test where I carried a narrowband, basically amateur radio transmitter in my car, and I was transmitting, and the colleagues were watching the bearings, and we could basically identify, and the route I drove was up to 5 kilometers roughly away in let's say urban environment, and the team here could basically identify. So we were coordinating. I was telling them I'm now at this bridge, and they could follow it on the chart, and I think we achieved the accuracy of better than 100 meters typically from a fixed stationary 5-channel DF in the 430 megahertz frequency band. What can also be done, it's also possible if you're talking about frequency hopper, there's a different way of displaying the DF results it's also a polar diagram, but then you have the frequency axis is mapped on the radius, and the azimuth is the azimuth or the angle, and this will allow for a nice grouping of the hops, and will help readily to identify the emitters of a frequency hopping signal. For triangulation, you always need 2 DF stations, of course.
Okay.
Yeah. So I mean, if I play back here, then this is computed. What you see here is computed in each time step. So of course it can also be used for a moving target, as long as it's not moving too fast, I guess. And now again, for this signal, it's also computed in each time step. The clustering is automatic. That's also a sophisticated algorithm running behind there.
Yeah, and just to give it a background, this is basically Janis is now working off an IQ recording, which was taken from the DF on the server, and he's now working through the pre-recorded IQ data.
For this recording, everything was ground-based though, so we just have the polar angle here.
Yeah, I mean, if the antenna is designed for it, we could also detect elevation, but it needs to be factored into the antenna design. We've also had cases where you're not always free to choose the antenna element locations, so we also have know-how how to exploit multiple antennas, and we have know-how how to simulate such situations.
Right now, in here you don't see this, but it's definitely possible to have a moving Yeah, I mean, right now here you would kind of see a moving target. I mean, this has a different angle than this. But it would also be possible when you have the moving DF antenna that you match the angles from the different locations. Like that's something we're currently working on, and then you could also do location